The definition of the cross product is not a very nice or very intuitive thing to try to remember. So this particular definition takes a three-dimensional vector, it takes two three-dimensional vectors and does something to it, and the result is going to be another vector. So this vector has three components. So I tried to separate the three components that comes out of here, but then it's not really, again, not very intuitive to look at these values and say, oh, okay, that's a cross product. So another approach to the cross product is that if you've taken any sort of linear algebra where you have to compute a three-dimensional determinant of a 3x3 matrix, this computation would be similar to doing something like that. So the idea behind this computation is you set up the vectors as rows, the second and third rows of the matrix, and the first row of that matrix is the I, J, K that we've discussed as the standard unit vectors in 3 dimensions. I don't.
So it's like sine 1 cosine another.
It has some of that action going on here. If you haven't taken a determinant of 3x3 matrix, this is essentially how it goes. You take the first element. In this case, it's not really an element, it's an actual vector, but we're going to pretend it's a number. And then you cross out the row and the column in which that element belongs to. And now you have a 2x2 matrix. And then you want to take the determinant of that 2x2 matrix. And to take a determinant of any 2x2 matrix, you multiply its diagonals. So this is A2 times B3. And then you multiply what we call the wings, and you subtract that, B2 and A3. You subtract that, and so that's the first term that you have here. So that takes care of your first component. Your second component in working out the determinant of a 3x3 matrix or larger matrix, you basically find little sub-cofactors. And what you do here when you get to the next step is that the signs are going to alternate. And since this is a 3x3 matrix, you basically have a positive, a negative, and then a positive. So that's why that middle term is a negative. And so when we're focused on that middle term, we're looking at the J component, the middle component of three-dimensional vector. Again, you cross out your row and column in which that vector belongs to. And then you're looking at the matrix A1, A3, B1, and B3, because you've crossed out the middle column. And then you take the determinant of this, it's A1 times B3 minus B1 times A3, but then you have a negative in front, and so those terms kind of switched. And then you do the same thing for the last one. The last one is going to be a positive. You cross out the row and the column in which it belongs to, and then you're looking at the submatrix. Okay, so you have to really be careful, meticulous on this, because there's a lot of room for little errors. You forget a minus sign, then your whole answer is wrong. And so you just have to be careful about doing the computation. So let's do a quick computation problem. where we're just looking for the cross product of a couple of vectors. Let's say your vector A is equal to 2, minus 1, 3. Your vector B is equal to 2, 2, 1. And then let's find A cross B. All right, so we get this set up. We start off with the I, J, and the K. To fill up our top row, we'll take the first vector 2, negative 1, 3 to fill up our middle row, and then 2, 2, 1, our last vector to fill up our last row. So this is going to be equal to, when we go through it using the determinant method, we're going to have an I vector. And then when we cross out the row and column in which that belongs to, we see a minus 1, 3, 2, 1. And so we'll figure that out in a few minutes. And then our next step is to look at the J component. Now remember, the J component will have a minus sign, so I'll put that minus sign there now. I'll have my submatrix I'll figure out in a minute. And then I have the J vector. So I cross out the row and column. And what do I have left? I have a 2, 3, 2, 1. So I'll figure that out. And then the last one is a K. In the K component, and we cross out the row and the vector, it looks like I'm going to have a 2, negative 1, a 2, positive 1. 2, 2?
Yeah. Are we going to have to memorize the matrix stuff?
You don't have to memorize anything, as long as you can do this.
Can we use our calculators? You know what I mean?
I don't know if you can use your calculators.
We have to do this for like 4 or 5-dimensional theoretical space.
Oh, no, we're not going. This is a 3-dimensional
Okay.
problem.
So
And
we memorize that formula at the beginning of oil this matrix stuff.
no, there's no. Nope.
So I have to learn matrices.
No, you have to know how to do the cross product. How you do it doesn't. I don't care, as long as you know how to do the cross product.
Okay.
Okay. So you could do it via the matrix. You can go back here and memorize a formula, or do it any way you want. If you can figure out a way to do it on your calculator, I don't care, as long as you can do this cross product. Okay. So what do we have? The determinant of this is negative 1. Negative 1 times 1 is negative 1, minus 2 times 3 is 6. So that's a negative 7. Is that right? And then the next one is there's a minus sign in front. So let's keep that minus sign in front. And then there's a 2 times 1 is 2. Minus 2 times 3 is 6. This is a negative 4 with a negative on the outside, so I think this is positive 4. Is that right? And then 2 times 2 is 4, minus 2 times negative 1. So this is a 4 plus 1 is 5. What? Minus 2? All right, so let's try that again. This is a 4 minus negative 2 is a positive 6. So that looks like it should be your matrix. I mean your cross product. It's another vector. Okay? So let's try to see if we can switch the order of the cross product to see if we see anything interesting about this. B cross A. So using the same vectors, but this time we switch the order. Everything that we've done so far has been commutative, which means if we switch the order, we still get the same answer. So let's see if this is also commutative. So we'll set this up, I, J, K, 2, 2, 1. That's your B vector. It goes first. And 2, negative 1, 3. Okay? So let's see if you know how to do this already. I'm in the I direction. That's the first component. I'm going to cross out the row and the column, and then I'm taking the determinant of this. So I have a 6 minus negative 1, 7. Next step, I'll have a negative in front of this, and then I have a 6 minus 2. That's a 4, right? With my negative sign. And then now the last step, in my K direction, I have negative 2 minus 4. Okay? If you can, see if you can do the calculation that quick instead of having to write out this thing all the time. All right? If you're stumbling and getting the wrong answers in your homework, maybe pause for a minute, do the calculation by hand the long way or whatever way, and then make sure you're going to be able to do this. So what do we notice about A cross B versus B cross A? It's the same vector except there's a negative in front of it, right? So that's going to be one of the important properties of the cross product. The cross product is not commutative. You switch the order, you don't get the same answer, but it's really close. You're off by a negative sign. So sometimes they call that anti-commutative. Cross product is anti-commutative. Okay. All right, let's examine a couple of other properties that are important to the cross product. Some would call it a definition. Some would actually go ahead and try to prove this. We will call it a definition or just the property that we're not going to prove. And similar to the dot product, there's also a definition of the cross product that has to do with an angle between the two vectors. So notice that the cross product is actually a vector. And so in this redefinition, they're taking the magnitude of the cross product because those angles with the sines and cosines can only be dealing with scalars. So we have the magnitude of the cross product is equal to the magnitude of A, magnitude of B, but this time it's looking at the sine of the angle between them. And if we call that the definition, we don't have to prove it, then there's going to be a few other things that follow. So sine of the angle between them. So this next statement tells us that if we have a vector A and another vector v going in the same or maybe the opposite direction, if they're parallel, then their angle is either 0 or if it's going the totally opposite direction, it's 180 degrees, right? What's sine of 0? What's cosine of 0? I meant, what's sine of 180 degrees? 0. So it turns out that sine of 0 and sine of pi are both equal to 0, which means the cross product of two vectors that are parallel to each other will be equal to 0. Now, when I say 0, the cross product, remember, is a vector. So when you say 0, you actually mean the 0 vector, the 0 with an arrow on top. Well, technically, it's not going anywhere, so I don't know if you would define a direction for that. 0 is this special number in vector fields that kind of allow you to not have a direction. Okay. The length of the cross product is the area of parallelograms spanned by A and B. Again, without proving this, we can use this definition to prove it, and we can do this. Well, I guess you can look in the book to see the actual proof. But if you have these vectors A and B, and then you extend this as a parallelogram that's spanned by A and B, you can find the area of that parallelogram by taking the magnitude of the cross product. Now, if you remember the area of the parallelogram, it's like something to do with, I don't know, the base times height. It's really just a rectangle, right, that's been kind of skewed, and then it's the same base, same height business. So if you think about it or sit down with a piece of paper and write this out, you can actually prove this if you know this information, that the length of A cross B is equal to this. And this, in fact, will give you the area of the parallelogram. Okay? So it's the magnitude of A times the height, and the height will be like something like B in the cosine or sine of theta. All right, there's one more very, very important fact about the cross product that we're going to discuss. And for that, I'm going to go back to, we can go back to this example, but I'm going to go back to the actual formula. And I'm just going to copy this. And what I encourage you to do is use the example that we did as 7, 4, 6, or 7, negative 4, 6, or whatever it was, and test it with this. So what I wanted to show you was the fact that the cross product, this is the cross product. If you have A and B that you're crossing, the cross product is actually going to be a vector, right? But there's something special about this vector. It's going to be a vector that's actually perpendicular to both A and B. So what I could do with that is take my A cross B, that's my new vector, which is equal to this big thing, and let's dot it. Let's dot it with the vector A. So A is A1, A2, A3. So I'm just going to go ahead and perform the dot product. A1 times A2B3 minus A3B2. Remember that the dot product is a scalar, right? So the next component in A is A2. The next component in A cross B is this thing, A3B1 minus A1B3. And then the last component of A is A3, and then I'm going to multiply that with the last component of A cross B. A1, B2, A2, B1. That's a lot of work, but let's go through it. This is A1, A2, B3 minus A1, A3, B2 plus A2, A3, B1 minus A1, A2, B3 plus A1, A3, B2 minus A2, A3, B1. If you look really carefully, A1, A2, B3, A1, A2, B3 with a negative. That's gone. Negative A1, A3, B2, positive A1, A3, B, A1, A3, B2. This is the positive one. And then, so that's gone. And then we have positive A2, A3, B1, negative A2, A3, B1. So all these would end up canceling themselves out, and then you get 0. What does that mean when you take the dot product? We took the dot product. What does that mean when you take the dot product of two vectors and you get 0? They're perpendicular. So this cross product is perpendicular to A. And it turns out that if you try to cross it with B, you're also going to get 0. Is this 0 with an arrow or no? No arrow, because the dot product gets you a scalar. So this vector is perpendicular to both A and B. Wait a minute. In 3 dimensions, if I have two vectors, if I have two vectors A and B, how many vectors are perpendicular to these two vectors? There's one here and there's one down there. So there's two possible vectors that we were talking about here. It would be nice if we knew which one it was. How would we know which one it was? Right-hand rule. A cross B. So the A, you take your right hand and you wrap your right hand, your fingers around A first and then B, and then whichever way your thumb is pointing is going to be the direction of your vector. So if this red vector is A and this is B, my right hand rule says I'm going to wrap my right fingers around A first and then B, and so whichever way my thumb is pointing is going to be the cross product. B cross A means I take my right fingers, wrap it around B first, and then to A, and then I'm forced to have my thumb go upside down, and that's the other cross product. That is the same length as the other one, except going in the opposite direction. Okay? All right, we need to go on a field trip. We're going to walk to the Learning Center. Yes, you guys can leave from there.